So, in the previous lecture we had introduced metric spaces, and the last result we had proved was the following lemma. So, we introduced metric spaces and we saw how, given a metric space, we can put a topology on it, and we proved the following lemma. We proved that if A is a subset of X, which is a metric space, right? So then X belongs to A closure if and only if there is a sequence xn's in A with xn's converging to X. Okay. So, using this lemma, we will give a convenient criterion for a subset in a metric space to be closed. So, let X be a metric space and let A contained in X be a subset. Then A is closed if and only if it has the following property. So, if xn's is a sequence in A and xn's converge to X, then X is also in A. Okay. So, okay. So, let us prove this lemma. So, proof. Recall we had proved that A is closed in a topological space if and only if A is equal to A closure, right. So, we will use this criterion. Yeah. So, first let us assume that. So, it is enough to show that A is equal to A closure if and only if xn belongs to A and xn converges to X, then X belongs to A. So, first assume that A is equal to A closure, right. So, then we have to show that the set A, it has this property. So, let us see this. So, if xn's are in A and xn converges to X, then by the lemma we proved in the previous lecture, X belongs to A closure, right. And we are assuming that A is equal to A closure. So, this implies that X belongs to A. Thus, X has this property. Okay. So, conversely, suppose A has this property. This has the property that every time we have xn's in A and xn converges to X, then X is in A, right. So, we assume that A has this property and we want to show that A is equal to A closure. So, let X be an element of A closure. It is obvious that A is contained in A closure. So, we just have to prove the converse. So, we take an element X in A closure. So, by this lemma, by this lemma that we proved in the previous class, there is a sequence xn's in A such that xn's converge to X, right. So, by this property that A has, every time we have such a sequence, then X belongs to A, right, because of this property. So we have a sequence xn's in A and xn converges to x. So we have x belongs to A. Yeah. So this implies that. So this implies that x belongs to A. Thus A is equal to A closure. Right. So thus A is closed. So to check that a subset is closed, we just need to check that every time a sequence of points in that subset A, xn's converge to x, then we just have to check that this point x is in A. To check the continuity of a map between metric spaces, so that is his theorem. So let x and y be metric spaces, and let f from x to y be a map of sets. Okay, so then f is continuous if and only if for every sequence xn's converging to x, we have f of xn converge to f of x. So this sequence is in x and this sequence is in y, right? So this gives us a way to check continuity of maps between metric spaces, right? So let us prove this. So let us assume that we first assume that f is continuous. Right. So for every, and let xn converging to x be a sequence. Right. For epsilon positive, consider the subset, the open subset, the epsilon ball around f of x. Okay, so right. So here we have x, and this is f. Here we have y, and here we have this f of x. So we just take this open ball around f of x of radius epsilon, and we look at its inverse image, right? So since f is continuous, so its inverse image may be some open subset like this. It implies that f inverse of this open ball is open in x, right? And moreover, since x is in this open subset, right? So x is somewhere over here, and this is an open subset which contains x. So therefore, there is a small delta, a ball of radius delta around x, which is completely contained in this open subset. So this implies that there is delta positive such that this ball of radius delta around x is completely contained inside f inverse of this set. Okay. So as xn's converge to x, by the definition of convergence, right, there exists n such that for all n greater than or equal to n, these xn's are in this ball. So we have this sequence of xn's which converge to x. So after finitely many, all these xn's are going to be in this open ball B delta, are going to be in this delta neighborhood of x, right? So this implies that which is contained in this subset, right? So this implies that for all n greater than or equal to n, f of xn belongs to B epsilon f of x. and by the definition, so by definition of convergence, this implies that f of xn converges to f of x. So this proves one part of the lemma. Okay. So now let us prove the converse. So to prove the converse, it suffices to show that means we are given that f satisfies a particular property. It takes convergent sequences to convergent sequences, and we have to show that f is continuous. So to show that f is continuous, it suffices to show that the inverse image of a closed subset is closed when z contained in Y is closed, right? And to show that this is closed, we will use this lemma that we just proved, right? Or okay, not this lemma. So we will. So let's see. So to show that f inverse z is closed, we will show that f inverse z is equal to its closure, right? So let us pick, so let x be an element in f inverse z closure, right? So this implies that there is a sequence xn's converging to x where xn's is in f inverse of z, right? So xn is in f inverse of z implies that f of xn's is in z, right? So moreover, since f takes convergent sequences to convergent sequences, that's the property that f has. If xn converges to x, then f of xn converges to f of x, right? So as xn converges to x, this implies f of xn converges to f of x, right? Now z, so as z is closed, this implies that f of x belongs to z. Z is closed, f of xn is in z, and f of xn converges to x. This implies that f of x belongs to z, right? So thus x belongs to f inverse z, right? So we started with the point x in f inverse z closure, and we proved that x belongs to f inverse z. So this implies that f inverse z is equal to f inverse z closure, right? So this implies that f inverse z is closed, which implies that f is continuous. Okay. Okay, so that kind of brings us to an end of the second part of this course. So in the first part, we introduced the notion of a topological space and basic examples. In the second part, we introduced continuous maps between topological spaces, and we studied their properties. In the second part, we also saw we also defined metric spaces, which gives us a large collection of topological spaces, and large and most important collection of topological spaces. But now now we are coming to the third part of this course. So in this part, we will introduce topological properties of topological spaces, right? So the first property we are going to introduce is that of connectedness, right? So we okay. So recall two topological spaces are called homeomorphic if there is a bijective continuous map f from x to y such that f inverse is also continuous. Right. So, two topological spaces are the same. So, the word same is in quotes, right. Same as in, as far as continuous maps are concerned, they cannot be differentiated if they are homeomorphic. Yeah. So, it is natural to ask, it is natural to try and classify topological spaces up to homeomorphism. Right. For instance, we can take the interval 0, 1 and we can take the disjoint interval 0, 1. I mean this topological space which is the disjoint union of two intervals, right, and we can ask, are these homeomorphic? Right. So, if we can find some topological property which 0, 1 has and this disjoint union of two intervals does not have, then it would mean that these two cannot be homeomorphic, right. So, we will introduce this notion of connectedness now, which will help us distinguish between two topological spaces. Okay. So, in this lecture, we shall introduce the notion of connectedness. Okay. Okay. So, definition. Let X be a topological space. Suppose there are non-empty open subsets U and V. So, they are non-empty, both of them, that is important, such that so U intersection V is empty, they are disjoint, and X is the union of both these, right. So, then we say that X is disconnected. Okay. Otherwise, if X is not disconnected, then we say X is connected. Okay. So, immediately, so we have this property, we have defined this property of topological spaces. So, we can ask the following questions. So we can ask, is R connected? So R is with the standard topology. What about Rn? Again with the standard topology. What are the connected subspaces of R? Is there a nice way to describe these, right? Or for that matter of Rn, right? So 3, if X and Y are connected, can we say something? So one of the topological spaces we constructed out of X and Y is the product about the connectedness of X cross Y. Then we saw various examples, right? Connectedness of GL and R, SL and R, ON, SON, GL and C, SL and C, and so on. UN, right? What can we say about the connectedness of these objects, right? So in order to answer these questions, we will need to develop some results and tools which we can use. Yeah. So okay, so let's begin that. So the first proposition we are going to prove is, let U contained in X be dense. Right. So if U is connected, then X is connected. Okay. So let us prove this. So let us assume that X is disconnected and arrive at a contradiction. Okay. So as X is disconnected, there are non-empty open sets U1 and U2 such that, which are disjoint such that we can write X as a disjoint union. X is a disjoint union of U1 and U2, right? So now we simply intersect both sides with U. So intersect both with U to get U is equal to U intersection U1 disjoint union U intersection U2. Right? So as U is dense in X, so as U is dense in X, this implies that U intersection U1 is non-empty and U intersection U2 is non-empty, right? But this shows that U is disconnected, which is a contradiction. Right. So this implies that our hypothesis is wrong, so that means X is connected. Okay. So as a corollary, we have let A contained in X be a subspace if A is connected, then the closure is connected. Right? Proof. Recall that. So when we talk about A and A closure, all these are subsets of X, and we are always giving these the subspace topology. So recall that we had proved that A is dense in A closure. Yeah, so applying the previous proposition, implies that A closure is connected. Okay, so we will end this lecture here.